Hi everyone. So I'm here to, I guess, chair the session with Dimitri presenting. So he will be talking to us about his latest research on introduction to formal evaluation of probabilistic forecasts in actuarial practice. So for those of you who don't know, Dimitri is a director of analytics at Insurance Australia Group. He has a particular interest in the advancement of practical actuarial methodology and its realignment with modern advances in optimization and machine learning. His other interests are in market design and risk theory. Dimitri has a PhD in computer science. So maybe we should get started. I'll hand it over to you, Dimitri, to kick off.
Yeah, well, thanks, Yang, for the introduction. And yeah, everyone, thanks for dialing in as well. Hopefully, this session's of some interest. So what we'll be covering off is, I guess, formal approaches to verification of forecasts, and in particular, probabilistic forecasts. I mean, when you think about the much of the output of the actuarial work, it can be described as forecast of sorts. For example, regression models, stochastic reserving, natural catastrophe, and capital models all generate forecasts that associate probabilities with some possible outcomes. However, very often forecasting also involves judgment or adjustments to the recommendations made. So any formal system of verification can really only rely on the stated forecasts and the actual outcomes. You can't really look into the process that was used to generate the forecasts themselves. Also, I guess so-called predictive analytics, so it's probably became popular over the last 10 years, also, I guess, embraced what you could call empirical verification. Usually there it's called out-of-sample model validation or cross-validation, where you create this sort of situation artificially. You have all the data up front, but you don't look at it. And you use that sort of as a verification set. Whereas, of course, with traditional forecasting, you forecast the future and then you compare your forecast with realized outcomes only later. But these ideas can only be applied in predictive modeling, where we would use them to validate conditional predictive distributions. Okay, so what are some of the important properties of good forecasts? Yeah, imagine a forecaster who each day predicts the probability of rain for the following day. Then, given a history of past forecasts and actual outcomes, which would be rain or no rain, we can look at all the days where the probability forecast is close to, well, let's say 25%. And it can be expected that for a good forecaster, on those days that they forecast 25% chance of rain, the rain actually happens somewhere around that, maybe 23 or 27. And if that property holds, then we say that the forecaster is calibrated at 25%. And if the forecaster is calibrated at all levels for these binary predictions, then we say that the forecaster is well calibrated. So here, to describe this kind of more formally and build on it, it will need to introduce some notation. So let's say we have n historical forecasts in total, and for each forecast we've recorded the probability of a binary event occurring, as well as the actual outcome. So we're looking retrospectively. Forecasts are issued at k discrete levels. So let's say if we have 11, well, let's say if we have 9 levels, we could have probabilities of 0.1, 0.2, 0.3, and so on. So we're not looking at very, very precise probabilities. Within each bucket, we have the outcome. So OKJ is the jth outcome that occurred when we forecast kth level of probability. So finally, we have OK bar OK is the average frequency associated with the kth forecast level. And O bar is the overall frequency or climatological frequency. So let's say a particular location, it rains, let's say 100 days a year, it would be about 35%. So it's kind of to summarize that setup. This is how you could plot that information that you've collected. So this is what you call a calibration plot. On the x-axis, we have the fraction of all the forecasts at that level or below. And so it goes from 0 to 100%. The red line shows the actual forecast value for that bin. So let's say here we have some forecasts close to 0, and then we have a finer gradation towards the middle, and then we have the sort of a large value as well. And then the dashed horizontal line is the average frequency, and the gray line is the average frequency for each of the historical forecast levels. So this plot, as we will see, more or less summarizes the entire sort of quality of the forecasting system, close enough. So with this in mind, we can ask ourselves, how do we verify calibration? Well, it's quite straightforward to do on this plot. We just compare the forecast levels, which are FK, the red line, with the gray line, which is the average frequencies associated with each one of those forecast levels. And if they're sufficiently close, we have to define how close that is. We have the we can say that forecaster is well calibrated. It would also be nice to attach a numerical value to the quality of calibration, and that quantity is what you'd call reliability. It's literally just the distance between the forecasts and frequencies for those forecast levels. So the shaded area, and then we square the individual values. Or at least that's one way to define the distance. Once we've, if we are not satisfied with the calibration of the forecaster, this can generally be fixed by post-processing of forecasts, so that the sorry, So that let's say if we have a forecaster who predicts 0.5%, 50% for certain outcome, but the outcome occurs only 40% of the time on average for that forecast level, we can just, every time we get a 50%, we can treat it as a 40%, and that will kind of remedy the issue. So, however, it's important to realize that calibration is not by itself sufficient to assess forecast quality. A forecaster predicting simply the long-run probability of rain each day, regardless of current meteorological conditions, would still be calibrated, but it's not very helpful. We want the forecaster to vary their forecasts depending on conditions, and for the outcomes to, on average, be different for different forecasts. The degree to which the forecaster is able to differentiate between likely and unlikely outcomes is called resolution. And we can also see it on the calibration plot. Here it's defined as the distance between the realized frequencies for different forecast levels and the average frequency. So how much better than just the overall climatological average is the forecaster able to do? This is the yes. So another quite straightforward quantity. Now, to evaluate the overall quality of a set of forecasts, we really should combine reliability and resolution. Just by convention, reliability is low for the numerical value is low for a highly calibrated forecaster. So that's perhaps a bit confusing. And the and we have the resolution is high for the forecaster who can differentiate outcomes well. So we just have to change the sign on resolution for them to kind of go in the same direction for the good for a good forecast. This is all done purely due to convention. And actually, with some, I omitted quite a few steps here, but with a fair bit of rewriting, we are able to, I guess, to see that what we get or what comes out is essentially the just your regular mean squared error. In the kind of forecasting literature, mean squared error is called Breuer's score. It's still used to this day, although mean squared error comes up as well. Plus this additional term, which doesn't actually depend on the forecasts themselves. It remains the same no matter what the forecasts have been. It is just the variance of the climatological distribution. So it's really quite remarkable. We saw that reliability and resolution can be derived from the simple calibration plot, and in fact, the mean squared error of the entire set of forecasts is just the sum of those two areas plus plus another term that does not depend on the forecast. So there's very close connection between what we think as kind of statistical errors, and we'll also see later log likelihood, and reliability and resolution ideas. With this in mind, we'll now look at the I guess where did this another way to think about the kind of ways to assess or score forecasts. The original work in this area, specifically the development of pre-score, was to find a formal metric that would encourage weather forecasters to report probabilities as accurately as possible and without incentives for deliberate distortion. So the idea was actually to have formal metrics where the forecasters would have a certain track record, and they would get a metric that is being tracked over time, and there would be some performance bonuses associated with keeping the metric below certain levels. So really quite a formal system. And the idea, but at the same time, they didn't want forecasters to what you might call game the system with the because with certain setups, it's possible to set up incentives in such a way that people would choose certain options deliberately to increase their rewards rather than to report the true probabilities. And with weather forecasting, it's really true probabilities what are important, because it's up to the users of the forecast to try to work out what makes sense for them. And this is a really simple setup. So the forecaster would like to issue a forecast F. So it's just a number in this case, it's just the probability of a binary event. But so as to minimize the score, or the kind of like the penalty that would incur on the scorecard. And if the forecaster believes that the kind of true probability of event occurring is PO, that's forecasters' kind of best belief about the outcome. Then if they were trying to minimize their score with that knowledge of P0, they would choose the forecast to be the minimum of the expected value of forecast minus the outcome squared, with an expectation is with respect to this their true belief. So after some straightforward manipulations, so taking derivatives of that with respect to f, setting it to 0, we find that indeed, if our penalty is the squared error, then the forecast that minimizes the score is the true belief. So that's quite a useful result. And I guess that's prompted this particular metric being adopted, at least in the United States, for weather forecast evaluation. Generally, of course, people like to generalize this. This area was especially popular with subjective Bayesians, like Savage, the others, because of course they had the idea of eliciting people's priors and so on. So they studied this area quite extensively, and they would ask questions like, well, so we have this squared error. Is this the only kind of score function that you can use to elicit true probabilities? And it turns out that no, there are in fact infinitely many such kind of score functions with these properties. And you can construct one very simply. So just take a function that is strictly concave on the unit interval. Yeah, if you think about it, just minus x squared is a strictly concave function. And if we set the score, so score is, in this case, is a function of two variables, the forecast and the outcome, which is the binary variable. And before we had, f minus o squared, but now we have the we have g of f plus the derivative of g at f times f minus o. So that's the general form of the score, and we can also quite straightforwardly verify that indeed for any such score, the minimizer of that expectation with respect to the true belief is the true probability. And just for fun, here are a couple of like functions g that first one, p minus p squared, that's the function that actually, if you expand things and so on, that's the one that gives you the Bria score, or the mean standard error, and this other concave function gives you the logarithmic scoring rule, which is logarithmic scoring rule is really simple. Everyone, it's just a negative log likelihood of observations under the forecast distribution. So that's another one, that another example. Well, it also turns out that and that's a really quite remarkable fact, that those reliability and resolution diagrams that we saw before, and the decomposition, you can obtain something like that for really any scoring rule for, well, binary outcomes, but even more generally. So here we have an example, the decomposition for the logarithmic score, and it's exactly in its form, it's exactly the same as what we've had before. So in this case, reliability is the distance between the forecast levels and the average frequencies for those forecast levels, except we are defining the distance slightly different, in a slightly different way from the way before. It was all squares, and now it's all logs. But if you plot the two one against the other, they're actually not that different at all. And then on the other side, we have resolution is the difference between the mean average probability, the sort of the climatological average, as well as the actual outcomes within the bins. So we're looking at how well the forecaster can deviate, can move away from just predicting the overall average. And uncertainty in this is something is called entropy, if you've seen that before. So what you can do with some, and unfortunately, notation ends up being really quite abstract, but you can in fact derive the, for an arbitrary scoring rule, you can derive this decomposition into resolution, reliability, and certainty. It's a bit messy with these expectations, and it's just a bit. It's not even always clear with respect to what the expectations are. But if you spend, I don't think you'd figure it right now, so I wouldn't worry too much, but they all kind of have the very same general flavor. So we define D as the sort of notion of quasi-distance. It's called divergence between distributions. A divergence is like a distance, but really not, because, well, it's always positive, and divergence between two points that are the same is 0, but it doesn't obey the triangle inequality, and it's not symmetric. So it's a very sort of lousy distance, and then you end up with decomposition into, again, resolution, which is the distance between the climatological distribution and the frequencies achieved at the forecast levels. And then you have reliability, which is the difference between forecasts and the average frequencies for those forecast levels. So it's exactly the same as we've seen before. So what this suggests is that there is this very, I guess, close relationship between reliability, resolution, and things like, let's say, log likelihood. In fact, if you take a log likelihood of just of a distribution with respect to and some data, you can break it up into resolution and reliability terms. And what's most important, if you have a forecasting system where reliability is not quite up to scratch, well, you can fix that part up without really rebuilding the entire system, which is just by transforming the forecasts themselves. And I'll show an example of that in a second. So with the so all of this before was for really binary outcomes. And you'd say, well, I never really work with binary outcomes, or I guess when you do the probabilistic forecasts aren't quite so important. So what we are looking at here is what you may call so here we are looking at verification of forecasts of continuous quantities. And unfortunately, the literature is quite a bit less complete, and what's there tends to be really quite abstract. And that's for the simple reason that before, the scoring rule was just a function of two real numbers, so very straightforward, you can plot it and whatever. Once you move into continuous variables, your score becomes it's a function of it that takes a distribution and a number. So you get, it basically becomes full of integrals and more abstract treatments. Essentially everything is kind of written in the language of functional analysis, which is fine if you kind of been exposed to it before, but certainly not the place to learn it for the first time. It absolutely isn't worth it. However, that's not really a showstopper, because in terms of those results actually are not quite as useful anyway, because as we'll see, to get to these quantities in the case of continuous variables, we need to do various approximations. So let's see, what can we say about reliability? Well, the simplest way for reliability to extend that to continuous outcomes is to look at the frequency with which forecast quantiles are not exceeded. So let's say, and what that means, let's say we forecast, we pick the, let's say 70th percentile of all of our forecasts, and then we want the outcomes to be less than the 70th percentile about 70% of the times. This is the standard QQ plot. Really, there's nothing else to it. So I didn't even bother doing an example. It's pretty boring. And then there is a close relative of the QQ plot, the PIT or PIT plot. At least that's one name for it. It's basically probability integral transform plot. And the idea here is also embarrassingly simple. So for every forecast we have this distribution. We work out what the cumulative density function of our forecast is. The cumulative density function goes from whatever the range of the random variable is to number between 0 and 1. And guess what? If we were to transform the observations outcomes OI with this forecast cumulative density function, if you're well calibrated, then what should come out is essentially a uniform distribution. And if we plot the histogram of Fi of OI for all i's, we should get a uniform distribution. So that's really all there is to it. Again, extremely boring. If you look at any of the kind of Bayesian regression papers or textbooks, they have quite a few of these, but it's not really necessarily clear what to do with them. But it's one of the practical challenges is that this approach doesn't work with discrete distributions like Poisson or distributions with non-zero with point masses like Tweedy with mass at 0. So there is a simple trick, I guess, to make it work again, where you can kind of fill in the gap in the whenever there is a jump in the CDF, instead of just kind of going from one value to the next, you jump somewhere randomly. So that gives you a nice uniform plot still. It's called quantized residuals, kind of Dunn and Smith. There is our implementation of it as well. However, generally speaking, this QQ PIT, that's plots. This doesn't really give you a full idea of what's going on, because they can kind of mask conditional miscalibration. To really replicate the binary case, what we need to do is we need to condition on different types of forecasts. Before, types of forecasts were just levels like 0.1, 0.2, 0.3, but here we are dealing with distributions. So we need to have a way of grouping forecast distributions together. And then for each type of distribution being forecast, that's where we really need to assess the calibration. And it may seem complicated, well, how I'm going to group distributions. However, quite a lot of distributions that are actually in use, let's say for GLMs, are really single parameter families. So a single parameter index, a single number indexes through all the your forecast distributions, so you can easily kind of bin them or essentially plot them. So that makes it quite easy. And then we have, so take kind of combining these two ideas, the augmented extended quantized residuals, and the that idea that you can actually order quite a lot of distributions. What we can do, we can do things like, let's say we have a bunch of forecasts, right? And what we are plotting at the top graph, our forecasts, they are not particularly well calibrated. We are plotting the CDF of the forecast applied to the observation versus the mean of the forecast, right? And we're dealing with distributions that are essentially parameterized by mean. Variance is a function of mean. So here we see so we get this graph where it's quite easy to see that something's not quite right. The traditional, like let's say if you're doing residual analysis for a GLM, the recommendation there would be to, let's say, refit the model, change the distribution that you're using. Maybe you can consider fitting a scale parameter, things like that. However, if you take this forecast verification approach, you say, well, it's okay. What I'm going to do, I'm just going to modify the forecast distributions. So what I've done here is I've fit basically a conditional density model to the top diagram. So basically it was like a conditional distribution as a function of the mean. So essentially what it captured was deviations from uniform. And then if we were to compose the forecasts that the system produces with this conditional distribution R, and it also has the mean as the argument. If we were to compose them with the CDF of the forecast that the system generates, we actually now get a system that is much better calibrated. If you look at the second plot, they're really, it all looks fairly uniform with a few deviations, but it's nowhere near as bad as it was before. And if you do this, like your objective quality just goes up. You can't really, if you have some validation and don't overfit and so on, you're just strictly making your forecasting system perform better, and you are not doing anything to the models that are generating the forecast. So it's really just a post-processing step. I mean, it is generally quite common to see when people, let's say, would recalibrate some sort of risk cost model or retention model and so on, where you kind of would level shift it to at least to get it to match more recent averages. So this is the same kind of idea, but for situations where you care about actual distributions being output and not just the means. So that's kind of the idea there. So it's, I think, quite a useful insight based on the general forecast verification thinking. Think about resolution, sort of ranking ability, and accurate labeling ability, which is reliability, separately. And you can actually fix reliability just based on some validation data, and you don't need to rebuild the whole thing. So yeah, when it comes to resolution, there really doesn't seem to be too much that's very useful for working with continuous variables. However, quite a acceptable way of dealing with it is just look at the means. So we can, let's say, you can get a sense of the resolution if you plot forecast distribution means versus actual observed averages within those groups of predicted means. You'll get something that's very similar to the calibration plot we saw before. But with the finally, here are some examples of scoring rules for the for continuous forecasts. So the first one is called rank probability score. Is essentially just a way to discretize continuous problem and turn it into several binary problems. So we pick a sequence of thresholds, like let's say it can be like, I don't know, 10, 20, 30, 50, and so on. Just some numbers that cover the likely range of the variable that we are forecasting, and we convert our probabilistic forecast into a number of binary forecasts. So we forecast the probability of the outcome being less than t for, according to that partition, t being drawn from that partition. And then our outcome, instead of being the continuous number, is just whether it was below the threshold or not. And this decomposes into the sum of Bria scores for those types of events. And if the partition becomes finer, the inner sum becomes the integral, and you get this what's called a continuous rank probability score. It's also the one, there's several R implementations of it as well if you want it. It's, to be honest, to me, it's unclear whether you'd want to use these in practice, because for most applications, you're probably better off with the logarithmic score, which is the extremely simple. It's just the sample average of negative log likelihoods of the observations under the forecast distributions. So it's exactly the same as the log likelihood you get when doing maximum likelihood estimation. And indeed, the use of calibration checking together with logarithmic score seems to be emerging as sort of kind of best practice for the people who do probabilistic modeling. Most of the people who do it do essentially Bayesian regression, like Andrew Gelman and so on, that kind of people, hierarchical linear models, and people use Stan and so on. So they're doing these, if you will, objective validation of their predictive distributions. And this was also used in the recent a study by Glenn Myers, where he looked at the North American Insurance Commission has released completed triangles for 200 companies and 5 or 6 lines of business. And what Glenn Myers did, he tried to run a range of stochastic reserving methods on the data and see whether predictions that came out actually matched the the bottom part of the triangle that he also had, and he could do it across like over 1,000 triangles. So that's some pretty interesting conclusions in there. But what he used there, essentially looking at probability integral transform plots together with the logarithmic score to get a sense of discrimination ability. Because of the specularities of the data, they had to do leave one out, cross-validation, but this is not strictly necessary. So that's, I guess, the conclusion of the presentation. So probably the main takeaway is that when you think about forecasting, there are 2 properties that define a good forecast: reliability, which has to do with how well your predicted probabilities match observed frequency of outcomes at those levels, and resolution, how well you're able to separate low probability events from high probability events. These 2 concepts link very closely to scoring rules, which just all the error functions you're familiar with: squared error, negative log likelihood, and in particular that if you have probabilistic forecasts, by doing recalibration, you can pretty much, you can quite frequently improve its performance without necessarily, making some large modifications to the system. And in general, what you think about as traditional, I guess, regression diagnostics, this is exactly the same thing as regression diagnostics, but done out of samples. So if you want to bring in if maybe if you're like people doing machine learning, black box models, decision trees, neural networks, it's somehow not customary to look at the residuals of those models. And if you did, it's unclear what you would do with them. However, here it is very clear. You don't check residuals in sample, because in fact you might have overfit in sample, but you check residuals out of sample. And in particular, if there are problems with reliability, well, you just modify the distribution. So you recalibrate the predictive distributions. So that's the all for my talk.
Okay, cool. Thanks for that, Dimitri. I think it was very well presented, and certainly had a lot of content for everyone to think about in relation to their own modeling work. By the way, Dimitri, I think we can't see your screen. Oh, now we can.
Yeah, okay.
Okay, cool. So we're now in the question and answer session, and yeah, happy to take any questions, and then we'll have the presenter answering them. So is there meant to be questions coming through? Because I didn't see anything.
Oh, you can ask something.
Okay, cool. I'll ask some stuff. So yeah, so in your equation and conclusion, you mentioned about the two integral parts of the yeah, in terms of assessing the goodness of the forecast. One being the reliability, the other one being the resolution. Yeah, is there one that's more important than the other? I guess you would want both to be good, and it's certainly not necessarily a trade-off if the if the model is really perfect. So yeah, so what's the general rule of thumb in terms of I guess would you target more of a good reliability, or would you care more for a good resolution? I think if we put it in another way, do we want a lot of differentiation within the segmentation of the risk, but without stuffing the order up? And also at the same time, we want to make sure that on average we're hitting the actuals as well with our prediction for each cohorts. Yeah.
Yeah, I mean, I think, well, if you link it, so there are probably two parts to this. In terms of forecasting, I mean, I'd say it's definitely the resolution, so ability to rank, that's the most important. That's where the actual skill of the forecaster lies, because as we saw, to ensure good calibration, well, you can just predict some kind of long-run averages or some kind of trended averages, which is depending on the environment again, right? So with climate, it's perhaps, well, at least used to be in the 1950s, not such a big deal. But there is this, of course, there are also trends and so on. So, but it's generally quite straightforward to fix the reliability component, and by doing recalibration, that's a straightforward kind of low effort operation. Whereas resolution, that's where the kind of skill of the forecaster really lies. So yes, you absolutely want high resolution forecasters, and in fact, they can even predict the opposite, right? So of what's really going to happen. But as long as they do it reliably, that's really great, right?
Yes.
So, however, in insurance, I guess depending on insurance is a little bit different, because in insurance you actually paying you're actually paying money if you miss reliability, if you miss the reliability, if your if your forecast is significantly below the average cost of claims and so on, well, you're kind of losing money and so on. So somehow in insurance, reliability is really very important. So because that's really indicates your overall profitability, and resolution really acts through a secondary kind of selection mechanism, right?
Fairness of the rating scheme.
That's right.
Yeah.
And generally speaking, the rates, the variation in your relativities are not that. Well, it depends on, I guess, how competitive the market is. The more competitive the market is, the faster your deficiency in resolution will manifest itself. But if the market is not very elastic, then the kind of leakage from poor resolution is an offset just by the overall price level. So in insurance, there's another dimension to this. In terms of which comes to kind of competitiveness and price sensitivity.
Yes. Okay. We actually have a question from the audience. Dominic Rowe is asking, thinking about climate change as a specific area where this topic may be of particular interest, is there any complication in separation of resolution reliability when an underlying hidden trend or paradigm shift is occurring?
Yeah, I mean, and that's a very good question. I mean, it's actually very similar to things like, just to give you an analogy, like this isn't particularly well suited, I guess, for the challenge of climate change. It would come through primarily as, I guess, issues with reliability. Like a good analogy for climate change is probably something like maybe claims inflation in insurance. It's kind of gradual and it affects things in an unknown way, or it can be gradual or sudden, yes. But there's your historical data isn't really going to help you very much. And I mean, and usually, but inflation, again, usually doesn't really affect your relativities so much. It mostly affects the overall level. So that's kind of probably a way to think about. And I mean, when it comes to, let's say, weather forecasting, there still will be a lot of variation in local weather, day to day. And that variation swamps the climate change caused a variation on any given day, but over a longer period of time, I mean, a kind of cumulative trend can really kind of disrupt those patterns. But if you look at validating daily forecasts, that wouldn't really come through in that, not unless you have very long data set. I think, yes, probably similar to how you think about inflation when dealing with setting relativities.
Mm-hmm. So I think that's it from the audience. Maybe you can ask another question. So in your presentation, you mentioned that, okay, if you're off in terms of reliability, it's kind of like a quick fix. You can recalibrate. But if you are, not that good in resolution, then, it probably takes a bit more effort to fix up the model and stuff. And I guess in terms of remedies there, it's about going back to the model themselves to evaluate the ranking or the segmentation, just like how you would do it in a traditional setting, like through actual versus expected, by looking at the different drivers in the model and figuring out what is not aligned with experience, or if the model is even robust enough to cater for the for this kind of setting in general. Maybe the model needs to be significantly remapped in terms of what variables you include, as well as the model structure itself.
Yeah, I mean that's right. I mean, because this kind of forecast, all the theory of forecast verification really just doesn't try to examine where the forecasts come from. So that's generally specific to the individual practice area, right? Even in insurance, well, you have stochastic reserving, you have rating, you have CAT models, and so on. So it's not, those are quite distinct, right? And the way you try to improve each one of those would be quite different.
Yes.
So it kind of very much depends on the model structure. However, I mean, one thing that you can take away, I think, from this is that, in particular, if you look at the score decompositions, so I mean, maybe like, for example, if you compute mean squared error or something like that for a pricing, for a pricing model, right, or for claims versus premium, you'll get some really stupidly high number, like 50,000.
Yes.
And
yes,
like,
and that's
what
probably
do you do
meaningless. Yes, meaningless
it
on its own.
seems meaningless. However,
Yes.
out of those 50,000, 49,950 is just what is called the uncertainty term, which actually doesn't depend on your model at all.
Yes.
So you can actually take that out, and you can get a better sense of at least how historically you can see how your resolution tracked, and whether if it's degraded, then you probably need to do something. So it does give you a bit more of a clearer view on what to what to do. But yes, not in terms of how to fix the models generating the forecasts, not in general.
Sure. Okay. We haven't got another question from the audience. Should we? Okay, we've got 3 minutes left. Is there anything else we can talk about?
Oh, I think we can wrap up. Yes, thanks.
Okay.
Thanks, Yang. Yeah, no, I think this is a very good good discussion. Yeah, well, thanks everyone. We don't really know who is online.
Who is actually here? That's right.
But that's all right. We'll thanks so much for joining. Hopefully you enjoyed it. And if things went clear, then I think the paper's gonna get uploaded any day now. So have a look at the paper, or if you're still interested in the topic, I mean, always happy to have a chat. So just reach out. And
I think it's an area that's getting a lot more scrutiny, because when models are deployed, people want to know, did the benefits stack up, and did it actually do its job? And this definitely provides a good avenue to assess that. And it's becoming more and more important as a lot more of the insurance organization, in terms of operation and pricing and various other aspects, become more data driven.
Yeah,
where decisions are made based on models.
Yeah, and just another plug, if you're interested in accurate, or if you will, inaccurate as it may be, assessment of benefits from at least certain types of analytics, specifically targeting, please join my session at 4 o'clock today, where I'm going to talk about some of the challenges in using modeling to target customers and so on with marketing and similar interventions.
All right, cool. That's good. So we'll wrap it up there. Thanks, Dimitri, and thank you for having us. And it's been great. Thanks.